Okay, recording has started. So, good morning, everybody, and welcome back to Math 115. Welcome, actually, to the final scheduled lecture for our class. So this week I will still have office hours today and on Wednesday, so you can come to those if you like. But there won't be any further like 8:30 lectures in our usual time. Okay, so for the rest of this week is for you guys really to study on your own, and of course I'll be available via email. So if you want to meet with me, then you can meet with me. We'll schedule a time, or you can come to office hours, or you can go to the Math Tutoring Center, or you can go to the SI sessions. So there's lots and lots and lots and lots of options for you to study. And that is kind of what the rest of this week is for. That's why we don't have class. It's for you guys to rest and study and prepare for your finals and take your finals. Okay, so let me share the screen. Okay, sweet. All right, well, before I started the class, I did just want to thank everybody for taking the course. Let's see, can you see my screen? There we go. Thank everybody for taking the course. I know that, this semester was definitely not the typical college experience that I think many of you were hoping for. And, I recognize that a significant increase in the level of effort is sort of required to make it through, sort of a challenging math course like this, even in the online format. So kudos to you guys. You're almost at the finish line, and if you can push yourself over it, I think that you guys will be in good shape. So thanks for taking the class, and yeah, that's what I had to say. So other than that, all I really planned for today was to address any student questions first and foremost, and then kind of carry on with this review. So why don't I start by checking with the class. Are there any major topics that anybody wants to cover during this last review day? Okay, well, if you think of any, then please don't hesitate to put them in the chat, or you can speak up on your microphone and let me know. Otherwise, I'm just going to yeah, sure, we can do question 18, no problem. Okay, question 18, let's see. Ooh, this looks wild. Interesting. Secant is, yeah, okay, cool, interesting. Yeah, we can definitely try this. Okay, so we want to verify the following identity. So we have an expression here. The right-hand side looks like negative sine squared of x, and the left-hand side we have this abomination of a fraction. Okay, and this fraction is involving cosine and secant, but further than that, there's something that's really striking about the left-hand side here, I think. What's really striking to me is the fact that these identities, the input here is negative x. Okay, so that's what immediately jumps out at me when I look at this problem. So, you know, we had the double angle identities and the half angle identities for handling things like when we had a 2x in here, or say a 4x or stuff like that. You know, we can reduce the power, or we can reduce the angle, or we can increase the angle. But here we actually have a negative angle. And that's a little bit troubling to me because the right-hand side and the denominator are expressed in terms of a positive angle x. So that's troubling to me. So my initial thought when I see something like this is that, well, I wonder if there's a way that I can rewrite each of these two expressions as some trigonometric function with just an x. Okay, so let's try it for cosine. So the question mark is here. That's what I'd like to know. And what I'd like to put here is cosine of negative x. So does anyone remember if there were any identities which would relate to expressions where on one side we have the input is negative x, and on the other side we have that the input is positive x? Okay, this is going to return back to our basic identities. So let me see if I can sort of demonstrate how I might try this on an exam. Yeah, we had a special word for them. They were the even and odd identities. The even and odd identities. So let me show you what I mean. So if I was going to try to figure out if there was an identity which looked something like this, which I'm motivated to do because I've never seen these types of identities before where we get a negative x in there. So I want to convert everything to just be about x so that I can be on kind of stable ground. So what I would do is I would go back to our notes on trig identities. Maybe it was week 14, I don't know. That's SOHCAHTOA. I think I need to go back another week. What is this? This is not that. Sorry. Here we go. Here's some double angle identities. I'm getting closer. I'd scroll back through all these identities and look for something which looks like what I'm looking for. And the first place I would start is with the fundamental trigonometric identities. If I didn't find one here, then I'd go and look at the other identities like the sum and difference identities, or the product identities, or the double angle or half angle identities. But there's one here actually that's already going to help us, because we can see here that cosine of negative x here, that's what we initially had, right? In fact, we have another expression. Okay, we have another expression in our fraction, which was secant of negative x. So what I'd like to do first is use these identities to sort of convert what we have in our fraction to be more familiar. Okay, I'm always trying to make it look more familiar than it is already. Okay, so I want to use these even and odd identities. So this was something that we learned, was that all of the trigonometric functions are odd except for cosine and secant. And those functions are going to be even functions. Okay, remember if we looked at the graph of a sine function, what did it look like? Sine function looks something like this. So like if you take 2 points like x and negative x, then the height of the function at each of those points is going to be the opposite of one another, right? So we get that identity that like sine of x is equal to negative sine of negative x. That was what it meant for a function to be an odd function. In other words, it's symmetric about the origin. That's another way of thinking about it. Okay, but for the cosine function looks like this nice bell shape, which is symmetric about the y-axis. So cosine x was an even function. And so therefore 1 over cosine x is a even function as well. Okay, so that's really a very clever identity that is going to help us a lot here. So I'm going to replace cosine of negative x by something more familiar. How about cosine of x? And I'm also going to replace secant of negative x by secant of x. Okay, so this was really just an extra layer of confusion to see, well, are you aware of how to treat with a trigonometric function when the input is a negative x? And the answer is yes, it's one of our fundamental identities. We look at the even and odd identities, and those apply quite directly. So we just replace cosine of negative x by cosine of x using that identity, replace secant of negative x by secant of x using that identity, and we arrive at cosine of x minus secant of x divided by secant of x. Okay, and now I'm just going to proceed pretty much as normal. I'm just going to write secant as 1 over cosine. So I get cosine of x minus 1 over cosine of x divided by cosine of x. 1 over cosine of x. Should have left myself way more space here, sorry. And that's the same as just multiplying cosine of x minus 1 over cosine of x times the reciprocal of the denominator, right? So I'll do cosine of x over 1 instead. So dividing by a fraction is the same as multiplying by the reciprocal, so I rewrite. And I get cosine squared of x minus, well, cosine over cosine becomes 1. And I'm supposed to check if this is equal to negative sine squared of x. So to check whether this is true, I'm just going to add 1 over to the other side. And I'm going to add sine squared to both sides. The 1's cancel on the left-hand side. On the right-hand side, we're left with just 1. And on the left-hand side, we have sine squared x plus cosine squared x. So I forget who asked this question initially. Heidi. Heidi, what do you think about this final expression? True or not true? True. This is a Pythagorean identity. Okay, so we took our original identity and we rearranged it until we got something which we know is true. Okay, so these two statements, the first statement, which says all this stuff about this fraction, And this statement, which says sine squared x plus cosine squared x equals 1, really say the same thing, okay? The only difference is that we've rearranged it a little bit. Okay, this is like when on your homework, the teacher asks you to summarize the source without directly copying the source. And so instead of saying like he went to the store, you don't want to copy the Wikipedia page, so you say something like, to the store he went. Okay, these two things, they just mean the same thing. We're just saying them in a sort of a different way. Okay, so feel better about this problem, Heidi? Cool. Alrighty. So Jake, sounds like you had a question about one of the homework problems. Can you give me a little bit more info? I can try to get the book out. Do you remember what the homework problem was? Like the chapter or the section number? Or maybe you could paste it into the chat. All right, well, maybe while you're working on that, I'll do another problem. So Jake, if you can get me that section number and chapter, or get me somehow a picture of the problem, then I can get it up on the page and go through it for you, okay? Homework 13, question 11. Does it say what the section number is in the chapter? I might be able to find it on my math lab real quick. Homework 13, question 11. Assignments. Homework 13. No, okay, I can go to course home, manage assignments. Homework 13. Right. Review. Preview. Okay, I got it up here. So let me know if this is the right one. Looks like, yeah, 6.1.20. So this is, we're given the following statement. Cosecant theta is equal to 3. And they tell us, find sine theta. But we can do this even more. We could do this for cosine of theta as well. We can do it for tangent of theta. We can do it for secant of theta. And we can do it for cosecant of theta. I'm sorry, cotangent. Okay, so what do they tell us? They tell us that cosecant of theta is equal to 3. Okay, so what is cosecant theta defined to be? Cosecant theta is defined to be 1 over sine theta. 1 over sine theta. Okay, that's the definition of cosecant theta. This is a reciprocal identity. Reciprocal identity. Okay, so the way that I want to find sine is, well, I just rearrange this equation until I get sine theta. So I multiply both sides by sine theta. I get 3 sine theta is equal to 1. And therefore, sine theta is equal to 1/3. So sine theta should be equal to 1/3 by this logic. And this just comes from the definition of what cosecant means. Cosecant of theta is from the reciprocal identity equal to 1 over sine theta. So if I know what cosecant theta is, then I can find sine theta by multiplying both sides by sine, dividing both sides by 3, and then I'm done. So that's how I can find sine theta from this stuff. How they got 2 square root of 42. So yeah, my numbers are going to be different than yours, but I'll try to go through this for us. Okay, so now to find the other ones, I don't have any identities that are going to relate cosecant, relate cosecant to these guys. However, I have some information here. I have sine theta is equal to 1/3. Okay, sine of theta is equal to 1/3. And if we return to our original understanding of how the sine function was defined, the sine function was defined to say, well, if we put the angle theta inside of the unit circle, if we put the angle theta inside the unit circle, then the sine value is the height of the point on the unit circle. Yeah, cosecant equals 13. Then we would have gotten 1 over 13 for sine theta. Okay, fine. Why don't I switch it to be like B13 then? 1 over 13. Better? And we'll find all the other ones too. Okay, so sine of theta is the y value of the point on the unit circle. So here's what I'm going to do. I'm just going to draw a unit circle. And I'm going to put an angle theta in here. And the question says that theta is an acute angle. That means that theta is less than 90 degrees. So I just put the line y equals 1 over 13 here. And I find the point whose y value is 1 over 13. And then I say, okay, this is going to be my theta. And I know that this length here is 1. This is the point something, comma, 1 over 13. And then this length on the side here is 1 over 13. So if I want to figure out what the other length is, I can just use the Pythagorean theorem, right? So if I want to know what this number x is, that would be this length here. I can do x squared plus 1 over 13 squared is equal to 1 squared. So in particular, x squared is equal to 200 and, wait, hang on, 169. So 168 over 169. Okay, because 1 over 13 squared is 100 and 1 over 169. So I subtracted 1 over 169 from both sides and got the cancellation on the left-hand side, and then the right-hand side became 168 over 169. So then x is going to be equal to the square root of 168 over 169. Okay, so we have that triangle there. And then the x value, right, is defined to be the cosine function. So this is going to be the square root of 168 divided by 100, the square root of 169, which is going to be the square root of 168 divided by 13, which is going to be equal to, let's see, how do we simplify 168? Wolfram, help me. 168, maybe 12 goes in? Yeah, 12. 12 times 14. So 14 is irreducible. 12 has a 4 in it. We can take that out. We'd get 2 square root of 3 times 14 all over 13, which would be equal to 2 times, let's see, 3 times 14, does that get us our 42? I think so. Yep. 2 square root 42 divided by 13. So that is our cosine value. All right, and then tangent of theta is just going to be equal to sine theta divided by cosine theta. That's another identity. So I just take 1 over 13 and I divide by the cosine. So I get 1 over 13 divided by 2 root 42 over 13. And I get 1 over 2 root 42. So if you wanted to rewrite that, you could multiply the top and bottom by the square root of 42. Wait, hang on. 42 has... No, yeah, 42 is fine. So then we'd multiply the top and bottom by the square root of 42, and we get square root of 42 over 2 times 42, which would be equal to the square root of 42 divided by 84. Then for secant and cotangent, we're just going to use our identities again. Secant is going to be 1 over cosine, which will be then 13 over 2 square root 42. Multiply the top and bottom by square root 42 to rationalize. And we get 13 square root 42 divided by 2, 84, sorry. And then for cotangent, we just flip tangent, right? Cotangent is 1 divided by tangent theta. So this will be two root 42 over 13 divided by 1 over 13. Let me rewrite this as not 1 over tangent, but cosine over sine. That's another identity. That's really more like what I'm doing here. And then we cancel the 13s and we just get 2 square root of 42. So I'm guessing that this problem asked you to find the cotangent. Is that correct, Jake? Okay, so the first trick is to take your cosecant here. And since we don't have any, identities really relating cotangent and cosecant, actually we do. So we could use one of those Pythagorean identities. Let me go back and show you what that means. So another thing that you could have done is used this identity just right from the get-go. So if you were asked to find out what is cotangent of x, you could have done this thing where you say, okay, 1 plus cotangent squared of x is equal to cosecant squared of x. So what we would do is take our problem and say, okay, 1 plus cotangent squared of x is equal to cosecant squared of x. And I know what cosecant of x is. It's 13. So I get 1 plus cotangent squared x is equal to 13 squared. So I would get cotangent squared x is equal to 168, and therefore cotangent x is equal to the square root of 168, and therefore cotangent of x is equal to, well, 4 goes into this 42 times, so it would be 2 square root 42. That's another way you could do this problem. If you just had to find the cotangent, well, you can find an identity which relates cosecant and cotangent. But it's also easy if we can just find the coordinates of this point here on the unit circle, we can find all of the trigonometric functions because they're all just defined to be, well, sine is the y, cosine is the x, tangent is the y divided by the x, secant is 1 divided by the x, cotangent is x divided by the y, and cosecant is 1 divided by the y. That was all of our definitions using the unit circle. Okay, so if we have a definition of 1 over y is 13, then we can figure out what y is, and we can use the Pythagorean theorem to find out what x is. Okay, so 2 different ways of taking this approach. We can use our identities if we want, or we can use the unit circle and a little bit of geometry. Okay. Have I sort of addressed this to your satisfaction, Jake, or do you still have lingering questions about this problem? Got it now. Okay, great. Let's see. All right. Anybody else that has a question, please do go ahead and post it in the chat. I don't think I had seen anything else, so what I'm going to do for now is just carry on with the exam. But if anybody else has another topic that they want to discuss or a question, specific question, then please do post it in the chat and I'll divert my attention towards that. Okay. So in this problem, what do we have? We have some, oh wow, this is hideous. What is this? Oh, okay, we can do this, no problem. I got confused for a second. All right, so here we have an exponential problem. So we have 6 to the x is equal to 7 to the x minus 1. Okay, and let me just remind us of one of the sort of methods that we used for solving these equations. If we had something like a to the x equals b to the x, okay, what we tried to do first is check first if we can write both bases as a power of the same number. Okay, so for example, if we have something like 3 to the x is equal to 9 to the x, then we rewrite 3 to the x as 3 to the x, and we rewrite 9 as 3 squared to the x, and then we can use our power rule, which says that, well, 3 squared to the x is 3 to the 2x. And then we have 3 to the x equals 3 to the 2x, and therefore we can say that by taking the log 3 of both sides, or just by intuition, that x should be equal to 2x. And that would give us that then x is equal to 0. Okay, so we can do that if we can express both bases, 3 and 9, as a power of the same number. Okay. All right, Kamar, I'll address that in just a sec as soon as I finish this problem. So the problem with this problem, which confused me at first, was that 6 and 7 are certainly not powers of the same number. There's no nice number. There is a number, but there's no nice number like an integer, which I could write at like 6 would be, you know, some power to the 2 and 7 the same number to the power 3 or something like that. So I'm in a little bit of trouble here. So I need to use my second method. So this was our easiest method if possible, and then the second method we used, if that doesn't work, is to use natural logs. Use ln. So the reason we use natural log is because natural log is something I can plug in on my calculator, and it does a great job of getting the things that I want to know out of the exponent. So I apply ln to both sides. I do ln of 6 to the x is equal to ln of 7 to the x minus 1. Oops, to the x minus 1. And then I can rewrite using the power rule that this is x times ln of 6 is equal to x minus 1 of ln of 7. And then I get x divided by x minus 1 is equal to ln of 7 divided by ln of 6. And that's something I can plug in on my calculator, and let's see what I get. Ln of 7 divided by ln of 6. Let's see what we get. Looks like this is about 1.08-ish. So then x is going to be approximately equal to 1.08 x minus 1.08 by multiplying both sides by x minus 1. So then 0.08x, no, negative 0.08x will be equal to negative 1.08, and so x will be approximately equal to 1.08 divided by 0.08. 1.08 divided by 0.08 is 13.5. So that's how I can solve that one. And if you want to really write out all the decimals of 1.08 da 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 da, then you can. I like using just these little approximately equal to squiggles. It's good enough to get a pretty good idea of what x should be. Okay, or if you want to leave it in really general terms, then you could do the following. You could get x is equal to ln of 7 over 6, ln of 6, x minus ln of 7 over ln of 6. You could leave it like that. Subtract over, you'd get x times 1 minus ln of 7 over ln of 6 is equal to negative ln of 7 over ln of 6. And therefore x is equal to negative ln of 7 over ln of 6 divided by 1 minus ln of 7 divided by ln of 6. And this is like a more exact answer for the problem. Okay. Before I move on to Omkamar's question, was there any confusion about this problem or any questions about this? I think it's been a while since we did these exponential problems, so it may not immediately come back to you that we should use ln for a problem like this. But if you return to our notes, that is exactly what we did. Okay. So now I'm going to address Omkamar's question, which is really sort of a behemoth of a question, but I think we can answer it in a couple of ways. The question is, why are tangent of x and cotangent of x pi periodic, parentheses, instead of the usual 2 pi periodic? Okay, all of our other trigonometric functions are 2 pi periodic, but these ones, for some reason, are pi periodic. These ones, for some reason, are pi periodic. Okay, so I'll give you one argument. Okay, I will give you one argument. The first argument we need is that we need two identities, which we didn't define. But I don't think you'll have trouble justifying that they are true. The first identity is sine of x plus pi is equal to negative sine of x. To see why this is true, examine the unit circle. If we have the unit circle, and I have an angle x, and this goes to a point, why don't I make this theta? So theta plus pi. So this is the angle theta, and then this is the point x comma y. If I look at the point at the angle theta plus pi, well, theta plus pi is directly across. Hopefully you agree with me. So this is theta, and then this is theta plus pi. And the point here will be directly across. We'll have the coordinates negative x comma negative y. So since the sine of an angle is defined to be the height of the point, and the height of these points are exactly the negative of one another, hopefully you will agree that this left-hand side, which says the height of the point corresponding to the angle theta plus pi, is equal to the negative of the height of the point corresponding to just theta. Okay, Kamar, do you buy that? Okay. So this one's true. In fact, it's also true for cosine. Cosine of theta plus pi is also equal to negative cosine of theta. Because guess what? If we just look at the x values now, and then we look at the x value of the point, which is exactly on the opposite side of the unit circle, it has the negative x, where these two, this x and x are the same, right? So what is this really saying? This is saying that the graphs of cosine and sine repeat in a certain way. It's saying that if we take a look at the graph of sine x, and we take a given point, x here. We take a given point x, theta maybe, and then theta plus pi will be here, and the height of this will be exactly negative of the height of the other one. Okay, if these are exactly pi units apart. Okay, and if we move our interval length here of pi or whatever somewhere else, again, we wait a second. Is this true? Yeah, it's true. I just drew this badly. So if we move our interval pi over a little bit, okay, then we're going to get a similar setup. Okay, for example, if I were to take this point here, theta, and then theta plus pi would be somewhere here. I just drew the graph kind of badly. Okay, so this is true because of basically this relationship. Okay, so if we have these two identities, I can get the last one quite easily in the following way. I can say, well, I want to check, is tangent of theta equal to tangent of theta plus pi? This is what I want to check. And the answer is yes, because tangent of theta plus pi is equal to sine of theta plus pi divided by cosine of theta plus pi. And using our two identities, we get negative sine of theta divided by negative cosine of theta, and the negative signs cancel. So this is just equal to sine of theta divided by cosine of theta, which is nothing but tangent of theta. So the reason that tangent is pi periodic and not 2 pi periodic is exactly because these negative signs cancel. Okay, so we just used the two identities which we just derived about cosine of theta plus pi and sine of theta plus pi being equal to the negative of one another. And that told us that if we take a look at tangent of theta plus pi, that's nothing but sine of theta plus pi divided by cosine of theta plus pi. And that's using our identities equal to negative sine theta divided by negative cosine theta, and that's equal to sine theta divided by cosine theta, which is equal to tangent of theta. So in the end, we get tangent of theta plus pi is equal to tangent of theta, which is exactly what it means for tangent of theta to be pi periodic. All right, Om Kumar, how do you feel about that proof? Are you convinced? Problem solved. Yeah, the other way you can think about it is that tangent of theta, right, is defined to be y over x. So if we take any point on the unit, well, okay, if we take any point on the unit circle, right, with a point like x comma y, and we look at its point which is directly across, it'll have the coordinates negative x negative y, well, the ratio of negative y over negative x is always going to be equal to y over x. Also, for cotangent, the ratio of negative x over negative y will be equal to the ratio between x and y. So this shows us cotangent of x is pi periodic. Okay. Cool. Hopefully you found that satisfying. All right. Well, it's 9:20, so I'm going to close for today here. But office hours start now and go until 10:30. So if anybody wants to stick around and see me solve more of this practice exam, or if they just have any questions themselves, then we can talk about those. Otherwise, thanks for coming to the class for the whole semester. I hope you enjoyed it. I hope you learned some stuff. And good luck on your studying for the final. Okay, so that's the end of class for today, but I will stick around and I will probably just carry on going through this practice exam for people if anybody wants to stay. So let's see here. Next one looks like an interest rate problem. Ooh, we should definitely not do 3 quarterly. Every year. Yep, thanks, Kamara, you too. Okay. Well, I'll finish up this this last problem just so that everybody who's watching the video can get some info on this interest rate stuff. Okay, I got to change the problem a little bit more. $2,000 investment is made in a bank that provides 5% interest rate. Set up the equations for the amount of money at the end of 2 years. For the following 2 scenarios, compounded every year and compounded continuously. Okay, so we need to sort of recall our 2 equations. So the first equation for compound interest, which is compounded annually or yearly, was, I think the way we wrote it is A of t is equal to A naught times 1 plus r to the power t, where A naught is initial investment, r is the rate. And we had another expression for compound interest, which is compounded continuously, and that was A of t is equal to A naught e to the kt, where now k is taking the place of the rate, and the initial investment is again A naught. So these were the 2 ways which we could compound interest that we learned. There are many more ways of doing it, but those are the 2 ways we learned. And the way that they both work is basically like the following. Well, we just check A naught is going to be for us our initial investment, which is 2,000. And R is going to be our interest rate. Of course, we're given 5%. Percent means over 100. Okay, percent means over 100. So R here is going to be 5 over 100, which is going to be 0.05. So if we want to find out how much we have at the end of 2 years, well, we want to know A of 2, and that's going to be equal to our initial investment, 2,000, times 1 plus R is 1.05, and we take all of this to the power 2. And that's our answer. So if we multiply it out, times 1.05, we get 25 times 2,000, 2205 dollars. Okay, and then for the compounded continuously, we get something a little bit different. In this case, we're gonna just get, well, what do we want? We want a of 2 again. But this time we're gonna do 2,000 times the number e, which remember, e is just a number like 2.718 something something. So we take this to the power 0.05 times t, which in our case is 2. So this is equal to 2,000 times e to the 0.1, because 0.05 times 2 is 0.10. So let's do it. If we do e to the 0.1, what do we get? 1.105 something something. And if we multiply that times, e to the 0.1 times 2,000, we get, and I have to use one of my squigglies here because I can't write all the decimals, 2210.34 ... So it turns out we make a little bit more money using continuous interest than we do using annual interest. Okay? Make a little bit more money that way. All right. Well, I think that's the last major formulas that I wanted to remind you guys of. So I'm going to stop the recording here, but I'm going to stay in here for office hours. So if anybody shows up, I will restart the recording and include that in the lecture for you guys so that you can review. Otherwise, I'll have office hours on Wednesday at the usual time. Don't forget there's the SI sessions. You can study for the test using those. You can also study using My Math Lab. Go to the Math Tutoring Center. They have a website. You can attend the Math Tutoring Center virtually, and another graduate student like me will help you. And if you want any other tips on how to study for this exam, please just email me and we can find a time to meet and chat, or I can give you some information over email. So thanks everybody for a great semester, and good luck studying for the final.